January 21, 1954. Groton, Connecticut. Temperature, 18 degrees Fahrenheit. First Lady Mamie Eisenhower stands on a wooden platform, gripping a champagne bottle wrapped in red, white, and blue ribbons. Below her, a black steel hull stretches 319 feet, longer than a football field. The crowd of 12,000 falls silent as her voice cuts through the winter air. "I christen the Nautilus." The bottle shatters. Champagne freezes on contact with the metal. But this isn't just another ship sliding into the Thames River. This is the vessel that will make every submarine in the world obsolete overnight. And standing in that crowd, watching without expression, is the man who willed it into existence. A 54-year-old Navy captain the establishment tried to force into retirement 8 years earlier. What you're about to discover is how one engineer rewrote the rules of naval warfare, built technology that shouldn't have been possible, and created a safety culture so perfect it hasn't had a single accident in 71 years. If stories of determination, innovation, and excellence fascinate you, hit that subscribe button. You're in exactly the right place. The date was August 9, 1945. Captain Hyman Rickover walked through the ruins of Hiroshima, Japan. 6 days after the atomic bomb. The city was ash and twisted steel. Bodies were still being pulled from rubble. The smell of death mixed with ozone and burnt metal. Rickover had spent World War II behind a desk at the Bureau of Ships in Washington, managing electrical systems for destroyers and battleships. Important work. Necessary work. Career-ending work. While his Naval Academy classmates commanded fleets and won medals, Rickover pushed paper. He was 45 years old. A captain who'd never commanded anything at sea. His personnel file contained words like difficult, abrasive, does not work well with others. The Navy had a phrase for officers like him: terminal captain. Men who'd top out at 06, serve their 30 years, and retire quietly to civilian life. That was Rickover's trajectory. That was his future. Except standing in Hiroshima, staring at what 64 kilograms of uranium-235 had accomplished, Rickover's mind went somewhere no one else's did. Not to weapons. Not to destruction. To propulsion. The mathematics were simple. Brutally simple. That bomb had released energy equivalent to 15,000 tons of TNT, 15 kilotons. That much energy from 64 kilograms of material. A diesel submarine carried 116 tons of fuel and could operate submerged for maybe 48 hours at 4 knots before batteries died. What if you could harness atomic energy, controlled, sustained fission instead of explosive release? You could build a submarine that never needed to surface. A submarine that could travel at 20 knots submerged, faster than most surface ships. A submarine that could patrol for months without refueling. You could rewrite every assumption about undersea warfare. There was just one problem. Nobody knew how to build a nuclear reactor small enough to fit inside a submarine hull. Nobody knew how to shield the crew from radiation in confined spaces. Nobody knew if reactor control systems would work at 400 feet depth during violent maneuvers. Nobody knew if seawater cooling would corrode reactor components. Nobody knew if steam systems could handle the pressures required. And the Navy didn't particularly want to find out. Rickover returned to Washington in September 1945. He requested assignment to the Manhattan Engineer District, the organization that had built the atomic bomb. Requested, not ordered. Because officers don't request assignments to theoretical research programs when their careers are already stagnating. The Bureau of Ships denied his request. Twice. Rickover went around them. He contacted the Office of Naval Research directly. He wrote to the Atomic Energy Commission. He leveraged the one thing he had in abundance: technical knowledge. While other officers talked in generalities about atomic power, Rickover submitted detailed proposals about reactor designs, shielding requirements, and cooling systems. He spoke the language scientists understood. In June 1946, The Navy reluctantly assigned him to Oak Ridge, Tennessee, temporary duty to study nuclear energy. 4 months. Just long enough to write a report that would be filed and forgotten. Rickover arrived at Oak Ridge and immediately understood something crucial. This wasn't a Navy problem. This was an engineering problem. And engineering problems could be solved if you asked the right questions and refused to accept impossible as an answer. Oak Ridge was a city of scientists, physicists who'd built reactors to produce plutonium for bombs. They spoke in theory. Rickover spoke in specifications. They talked about neutron flux and fission cross-sections. Rickover asked about pipe diameters and heat exchanger efficiency. They thought in abstractions. He thought in steel and water and pressure. The scientists explained why a submarine reactor was impossible. Too much shielding required. The weight would sink the submarine. Too much heat generated. Conventional cooling systems couldn't handle it. Too much complexity. You'd need PhD physicists to operate it, not sailors. Rickover listened. Then he started calculating. Not theoretical calculations. Engineering calculations. He measured the space available in a submarine hull. Calculated the weight budget for shielding using lead and polyethylene. Designed a pressurized water system that could transfer heat efficiently. Sketched control systems that sailors could operate after intensive training. By October 1946, when his temporary duty ended, Rickover had something the Navy didn't expect: a viable design. Not a complete design. That would take years. But proof that a submarine nuclear reactor was possible if someone was willing to solve approximately 10,000 engineering problems. Rickover returned to Washington with blueprints and calculations. He requested permanent assignment to develop nuclear propulsion. The Bureau of Ships' response was predictable. Denied. Nuclear power was a research curiosity, not a practical weapons system. The Navy had real work to do, building conventional submarines and surface ships. What the Navy didn't understand was that Hyman Rickover had just spent 4 months learning how the Atomic Energy Commission operated. And he'd discovered something useful. The AEC and the Navy didn't always communicate effectively, which meant if you were smart and careful and willing to work harder than anyone else, you could play them against each other. In December 1947, Rickover did something unprecedented in military bureaucracy. He got himself assigned to 2 organizations simultaneously: the Navy's Bureau of Ships and the Atomic Energy Commission's Division of Reactor Development. Same office, same desk, 2 bosses, 2 chains of command, 2 funding sources. The Navy thought they were lending an officer to the AEC temporarily. The AEC thought they were getting Navy expertise for their reactor programs. Rickover intended to use both organizations to build something neither had authorized: a nuclear submarine. His strategy was elegant in its simplicity. When the Navy questioned costs, he'd point to AEC funding. When the AEC questioned military applications, he'd cite Navy requirements. When both organizations wanted to slow down, he'd already moved to the next phase. By the time bureaucrats caught up, key decisions were irreversible. He established the Naval Reactors Branch in a converted warehouse on Constitution Avenue in Washington. Not at the Pentagon. Not at a Navy yard. In a temporary building with peeling paint and second-hand furniture. The symbolism was intentional. This program would succeed through work, not appearances. Rickover needed a team. Not the best-connected officers. Not Naval Academy ringknockers who knew how to navigate Pentagon politics. He wanted engineers who could solve problems that textbooks hadn't addressed. Men who understood that nuclear propulsion wasn't a theoretical exercise. It was 10,000 practical challenges that each had to be solved perfectly. His interview process became legendary. He would schedule candidates for 9 a.m., then make them wait until 2 p.m. without explanation. When they finally entered his office, the chair facing his desk had shortened front legs. Candidates literally sat off balance. The first question was always technical. Calculate the thermal expansion of a steel pipe carrying 550-degree water. No calculator. No reference materials. Just pencil and paper. If candidates gave approximate answers, Rickover would demand precision. If they requested reference materials, he'd ask why they didn't know the information. If they showed frustration, he'd note it in their file. He was testing technical knowledge. But more importantly, he was testing temperament. Operating a nuclear reactor left no room for guesswork and no tolerance for anger clouding judgment. One candidate, a lieutenant commander with a degree from MIT, answered every technical question perfectly. Rickover listened, then asked, "Why do you want nuclear power training?" The officer explained career advancement, technical challenge, serving his country. Standard answers. Rickover cut him off. Wrong. You want nuclear training because you understand that operating a reactor requires absolute precision, and you're someone who can maintain that precision under pressure. If you're here for career advancement, leave now. The officer left. He failed the interview not because he lacked knowledge, but because he lacked the mindset Rickover demanded. By mid-1948, Rickover had assembled 80 officers and civilians. They worked 7 days a week. 16-hour days were standard. Rickover would call meetings at midnight to review calculations. He'd read pencil reports and return them with notes like sloppy thinking or redo completely. His management style was brutal. He once told an engineer, "If you want appreciation, buy a dog. If you want results, work harder." But here's what his critics never understood. Rickover wasn't cruel for entertainment. He was building something that had never been built. One miscalculation in reactor shielding would irradiate the crew. One failure in the cooling system would cause a meltdown. One imperfect weld would crack under pressure and sink the submarine. Excellence wasn't obsession. It was survival. The first major decision was reactor type. In 1948, 3 designs competed: gas-cooled, liquid metal-cooled, and pressurized water. Gas-cooled reactors were efficient but required massive pumps. Liquid metal reactors used sodium coolant, efficient but chemically reactive with water. Pressurized water reactors were less efficient but used proven technology. Most nuclear physicists favored liquid metal. Higher operating temperature meant better efficiency. Rickover overruled them. He chose pressurized water not because it was theoretically superior, but because it could be built with 1948 technology and operated by sailors with 6 months training, not PhD physicists. The design was elegantly simple: uranium fuel rods in a pressure vessel surrounded by water. The water served 3 functions: moderator to slow neutrons, coolant to remove heat, and radiation shield. That primary coolant circulated at 550 degrees Fahrenheit under 2000 psi pressure, too high to boil. Heat transferred to a secondary loop through steam generators. The secondary loop produced steam at lower pressure to drive turbines. If anything went wrong in the secondary loop, the reactor remained safe because the loops never mixed. By 1949, Rickover had convinced the AEC to fund construction of a prototype reactor, the S-1W, or Submarine 1 Westinghouse. Not a small-scale model. A full-size replica of exactly what would go into the submarine. Every pipe, every valve, every control system. It would be built in the Idaho desert at the National Reactor Testing Station, where if something went wrong, the explosion would be far from population centers. The prototype construction began in 1950. But Rickover faced a new crisis. The Korean War had started. The Navy needed conventional submarines immediately. Congress was questioning why money was being spent on experimental reactors when diesel boats worked fine. And a selection board was convening to consider promotions to Rear Admiral. Rickover's name was on the list. But so were the names of officers he'd alienated, insulted, and bypassed to build his program. Hyman George Rickover was born January 27, 1900, in Macau Mazowiecki, Poland, then part of the Russian Empire's Pale of Settlement, where Jews were confined by law. His father Abraham was a tailor who worked 14-hour days in a shop that smelled of wool and kerosene. His mother Rachel Unger spoke Yiddish and Russian, but never learned to read. They lived in fear, not abstract fear, but practical fear of pogroms, conscription, and starvation. In 1904, that fear became specific. Violence against Jews was escalating. Abraham Rickover sold everything they owned, furniture, tools, Rachel's wedding jewelry, and bought passage to America. They arrived at Ellis Island in January 1906 with one trunk and $17. Chicago's West Side was where Polish Jews settled, and the Rickovers moved into a tenement on Maxwell Street. 3 rooms. No heat except a coal stove. Toilets in the hallway shared by 6 families. Abraham found work in a sweatshop sewing uniforms. Rachel took in laundry. Young Hyman, he Americanized his Hebrew name Haim, delivered newspapers at 4 a.m. before school. He learned English by reading those newspapers. Taught himself mathematics from library books because his elementary school teachers didn't challenge him. By age 12, he was reading calculus texts. Not understanding everything, but absorbing the logic, the systematic reasoning, the idea that complex problems broke down into solvable components. His high school teachers at John Marshall High School noticed something unusual. The boy didn't just memorize, he questioned. When a physics teacher explained that heavier objects fall faster, Rickover cited Galileo's experiments proving otherwise. When a history teacher stated that great men shape events, Rickover argued that economic forces and technology matter more. He was brilliant. He was also insufferable. In 1918, at age 18, Rickover took the Naval Academy entrance exam. Not because he dreamed of serving at sea, because it was free education. 4 years of room, board, and training that his family couldn't afford. He scored high enough to receive an appointment from Congressman Adolph Sabath, one of the few congressmen who'd nominate Jewish candidates. He arrived at Annapolis in June 1918. The other midshipmen, sons of Navy officers, descendants of Confederate generals, graduates of New England prep schools, took one look at this 5'6" Jewish kid from Chicago's slums and decided he was exactly what he appeared to be, someone who didn't belong. They called him Jew Boy to his face. They excluded him from study groups. Put him in silence, a punishment where classmates refused to speak to the target. They made sure he understood, you're tolerated because the law requires it, not because we accept you. Rickover's response was to become impossible to ignore. He studied while others slept. He mastered navigation, engineering, seamanship, ordnance, every technical subject. But he struggled with military bearing, proper deference to upperclassmen, and the unwritten rules of academy social hierarchy. He graduated in 1922, ranked 107th out of 540. Not brilliant, just competent. More importantly, he graduated in engineering when most midshipmen chose warfare specialties like gunnery or navigation. His early career was exactly what the Naval Academy establishment predicted: mediocre. He served on the destroyer La Valette, on the battleship Nevada, always in engineering spaces, never commanding anything. In 1929, he was accepted to Columbia University for graduate study. The Navy sent promising officers to earn master's degrees. Rickover earned his degree in electrical engineering in 1930. The Navy assigned him to shore duty managing power systems. During the 1930s, while his academy classmates commanded destroyers and cruisers, Rickover managed electrical grids at Navy yards. Important work. Technical work. Career-killing work. Combat command was the path to flag rank. Shore duty was where careers stagnated. World War II changed nothing for Rickover. He was assigned to the Bureau of Ships in Washington, managing electrical systems for the rapidly expanding fleet. While classmates fought at Midway, Guadalcanal, and Leyte Gulf, Rickover coordinated generator specifications and power distribution systems. He was promoted to captain in 1943, on schedule, but without distinction. When the war ended in August 1945, Rickover was 45 years old. A captain who'd never commanded a ship. His fitness reports praised his technical competence and criticized his interpersonal skills. The message was clear: serve out your time, retire, find work as an engineer at General Electric or Westinghouse. Then came Hiroshima, and everything changed. In 1951, Captain Rickover's name appeared on the selection board list for promotion to Rear Admiral. On paper, he deserved it. He'd established the Naval Reactors branch, convinced Congress to fund nuclear propulsion research, designed a reactor that might actually work. The prototype in Idaho was under construction, on schedule and under budget. The selection board met in July 1951. They reviewed Rickover's record. Brilliant engineer. Difficult personality. Confrontational with senior officers. Bypassed normal chains of command. Made enemies in the Bureau of Ships. Made enemies in the Office of Naval Research. Made enemies among contractors. Jewish. Immigrant background. Didn't fit the Navy's image of flag officers. The board's decision was unanimous: pass over. Rickover learned of his rejection through official notification, a terse letter stating he had not been selected for promotion. Under Navy regulations, officers passed over twice for promotion must retire. He'd get one more chance in 1952. If passed over again, his career would end. The nuclear submarine program would be handed to someone more manageable. Someone who knew how to work within the system. The Navy had made a critical miscalculation. They assumed Rickover would accept this quietly. They forgot that this was a man who'd survived poverty, anti-Semitism, and 30 years of Navy politics through one strategy: refuse to lose. The S-1W prototype reactor site in Idaho was 50 miles of desert northwest of Idaho Falls. In 1950, it was sagebrush, jackrabbits, and volcanic rock. No buildings. No roads. No infrastructure. Just flat emptiness where if something exploded, it wouldn't kill anyone who mattered to Congress. Rickover chose the location personally. He wanted the prototype far from cities for safety, but close enough to Idaho Falls for workers to live. He wanted terrain that could accommodate a full-scale submarine hull. The reactor would be installed in an exact replica of a submarine's reactor compartment, not a laboratory mock-up. Construction began in March 1950. Workers built a steel cylinder 30 feet in diameter and 40 feet long, the same dimensions as a submarine's hull section. Inside, they installed the S-1W reactor exactly as it would sit in an actual submarine. Every pipe, every valve, every pump. The only difference, the Idaho prototype was anchored to bedrock instead of floating in water. The reactor vessel was fabricated by Westinghouse at their Bettis laboratory near Pittsburgh. 8 feet in diameter, 14 feet tall. Steel walls 8 inches thick. Inside, uranium fuel rods arranged in a precise geometry, close enough for sustained fission, far enough apart to allow coolant circulation. Control rods made of hafnium could be inserted to absorb neutrons and stop the reaction. The engineering challenges were immense. Water at 550 degrees Fahrenheit and 2000 psi pressure required pumps that didn't exist. Westinghouse built them from scratch. Massive centrifugal pumps with special seals that wouldn't leak under pressure. The steam generators had to transfer heat efficiently without allowing primary coolant, radioactive, to mix with secondary coolant, clean. They designed tube and shell heat exchangers with thousands of thin tubes, primary coolant inside, secondary coolant outside. Every component was tested beyond operational limits. Pumps ran at 150% rated capacity. Valves cycled 100,000 times. Pipe welds were X-rayed. then sectioned and examined under microscopes. If a weld showed the slightest imperfection, a tiny void, a microscopic crack, the entire section was cut out and re-welded. Rickover visited Idaho every 2 weeks. He'd arrive unannounced, walk through the construction site, and question everything. Why was this valve rated for 2,500 psi instead of 3,000? Why did this pump installation use 4 bolts instead of 6? Why was this pipe support made of carbon steel instead of stainless? Workers learned that "good enough" didn't exist in Rickover's vocabulary. One welder recalled Rickover rejecting a perfect-looking weld because the X-ray showed a void smaller than a pinhead. The welder protested. That void would never cause failure. Rickover responded, "How do you know? Have you operated a nuclear reactor at sea during depth charge attacks? No. Then re-weld it." The reactor first went critical, achieved sustained fission, on March 30, 1953. The startup procedure took 6 hours. Step by careful step, operators withdrew control rods. Neutron counters clicked faster. Temperature rose. At 11:47 a.m., the reactor reached criticality. Chain reaction was self-sustaining. They ran the reactor at low power for a week, monitoring every sensor. Temperature distribution in the core. Pressure in the primary coolant loop. Radiation levels throughout the system. Everything matched calculations. They increased power gradually. 10%, 25%, 50%. Finally, on May 31, 1953, the S-1W reactor reached 100% power, 13,400 shaft horsepower, exactly what the submarine would need. Then came the torture tests. They simulated emergency conditions. Loss of primary coolant pump. Backup systems activated automatically. Sudden power increase. Control rods inserted within seconds. Stuck control rod. Remaining rods provided adequate shutdown margin. They ran scenarios that had never happened and probably never would, just to prove the reactor could survive them. Between June and December 1953, the S-1W operated for 2,500 hours at various power levels. It demonstrated that a nuclear reactor could fit in a submarine hull, operate reliably, and be maintained by trained sailors rather than PhD physicists. It proved Rickover's concept worked. But proving the concept and building an operational submarine were different challenges. The prototype sat on bedrock in Idaho. The actual submarine would roll in storms, dive to 700 feet where pressure crushed steel, and maneuver violently during combat. Would the reactor survive? Meanwhile, in Groton, Connecticut, the Electric Boat Division shipyard had laid the keel of USS Nautilus on June 14, 1952. The submarine was under construction, a steel hull being built around reactor spaces that were empty. Because until the Idaho prototype proved the reactor worked, there was nothing to install. The shipyard workers were building a submarine unlike anything they'd constructed. The hull was stronger, HY-80 steel capable of withstanding pressure at 700-foot depth. The reactor compartment was in the center of the hull, surrounded by lead shielding. The forward section contained crew quarters, control room, and torpedo room. The aft section contained turbines, reduction gears, and propeller shaft. By December 1953, the S-1W had operated flawlessly for 6 months. The reactor was proven. Westinghouse began fabricating the submarine reactor, designated S-2W, in a clean room at Bettis Laboratory. The reactor would be built in sections, transported to Groton under armed guard, and installed in Nautilus. If everything went perfectly, the submarine could be commissioned by late 1954. But Rickover still had one problem. He wasn't an admiral. And the Navy's selection board was meeting again to consider flag promotions. In January 1952, the Navy's flag selection board convened for the second time to consider Captain Hyman Rickover's promotion to Rear Admiral. Navy regulations were explicit. Officers passed over twice for flag rank must retire at 30 years of service. For Rickover, That meant mandatory retirement in June 1952. 6 months before Nautilus would be completed, 2 years before the reactor would be proven at sea. The selection board reviewed Rickover's file. His accomplishments were undeniable. He'd established the Naval Reactors program from nothing, designed a working reactor, built a prototype ahead of schedule and under budget, convinced Congress to fund nuclear propulsion, created training programs that produced exceptionally competent reactor operators. The board also noted the complaints. Rickover had bypassed the Bureau of Ships repeatedly, made enemies of senior admirals, insulted contractors, worked his staff mercilessly, refused to compromise on standards even when compromise was diplomatically necessary. One fitness report stated, "This officer is the most competent engineer in the Navy. He is also the most difficult subordinate I have ever supervised." The vote was taken. The result, pass over. Again. Unanimously. The decision was rational by Navy standards. Flag officers need to work within the system, build consensus, maintain diplomatic relationships with contractors and Congress. Rickover did none of those things. He was a brilliant engineer, but admirals need different skills. What the selection board didn't anticipate was the political explosion that followed. Representative Sidney Yates, Democrat from Illinois, learned about the decision from one of Rickover's supporters. Yates was furious. The Navy was developing technology that could revolutionize naval warfare, give America strategic superiority over the Soviet Union, and potentially win the Cold War. And they were forcing out the man responsible because he didn't play golf at the Army-Navy Club? Yates went to the media. Navy blocks promotion of atomic submarine Pioneer hit newspapers in February 1952. The story gained traction. Here was an immigrant kid who'd overcome poverty and discrimination, developed revolutionary technology, and was being punished for not fitting the old boy network. Other congressmen joined. Representative Carl Durham, chairman of the Joint Committee on Atomic Energy, demanded explanation from the Secretary of the Navy. Senator Henry Jackson from Washington called it bureaucratic stupidity. Editorial boards questioned whether the Navy was hindering its own modernization. The Navy responded that promotion boards are independent and based on comprehensive evaluation of candidates. Which was true. What they didn't say was that comprehensive evaluation included subjective factors like fits the naval officer image. By April 1952, the pressure was overwhelming. Congressional committees threatened to investigate the promotion system. Defense Secretary Robert Lovett received letters from senators demanding Rickover's retention. The Navy was facing a choice: promote Rickover or explain to Congress why bureaucratic culture mattered more than nuclear submarines. In July 1952, an extraordinary step was taken. The Secretary of the Navy directed the selection board to reconvene and reconsider passed-over candidates. This almost never happened. Selection board decisions were considered final. But political pressure had made the normal process impossible to sustain. The board reconvened. This time, with Congress watching and media reporting, they promoted Captain Hyman G. Rickover to Rear Admiral. The vote wasn't unanimous. Some board members resented congressional interference. But it was sufficient. Rickover was 52 years old. Most officers make admiral in their early 40s. His career had been saved by political warfare, not naval meritocracy. The message was clear. He owed his rank not to the Navy, but to Congress. And his enemies would remember. The promotion changed nothing about how Rickover worked. If anything, it made him more demanding. He now had authority to match his temperament. Officers who failed to meet standards were relieved immediately. Contractors who missed deadlines lost contracts. He created the Naval Nuclear Power School, 6 months of intensive classroom training followed by 6 months operating the Idaho prototype. The curriculum was brutal. Students studied thermodynamics, reactor physics, radiation biology, materials science, and electrical engineering at a level comparable to graduate school. They memorized every system in the reactor plant. Every valve, every pipe, every safety interlock. They could draw the entire primary coolant system from memory, with pipe diameters, flow rates, and pressure drops. Then came prototype training in Idaho. Students stood watches as reactor operators. They performed startup procedures, shutdown procedures, emergency procedures. They operated the reactor during simulated casualties, loss of coolant pumps, stuck control rods, steam leaks. They were tested constantly, and the failure rate was approximately 25%. Rickover believed that understanding why something worked prevented accidents better than memorizing procedures. One student recalled being asked why primary coolant pumps used mechanical seals instead of packing glands. The student explained that mechanical seals don't leak. Rickover asked, "Why don't they leak?" The student didn't know the engineering principles behind mechanical seal design. He was removed from the program that afternoon. This wasn't cruelty, it was mathematics. A reactor operator who doesn't understand seal design might ignore a small leak. That leak might indicate seal degradation. That degradation might lead to catastrophic failure. In Rickover's world, ignorance was lethal. By mid-1954, Nautilus was nearly complete. The S2W reactor had been installed at Groton. Systems were connected. The crew, 60 officers and men, had completed nuclear training. Commander Eugene Wilkinson, Nautilus's first commanding officer, had spent 6 months in Idaho learning to operate the reactor. Everything was ready. Except nobody knew if a nuclear reactor would actually work inside a submarine. The Idaho prototype proved the design. But Idaho was on bedrock, protected from weather, accessible to technicians. Nautilus would operate in the North Atlantic, diving to depths where pressure crushed conventional submarines, maneuvering during storms that tossed destroyers like toys. On January 17, 1955, the moment of truth arrived. January 17, 1955. Groton, Connecticut. 6 a.m. Temperature, 4 degrees Fahrenheit. USS Nautilus sits pierside at the Electric Boat Division shipyard, black hull reflecting the lights of tugboats maneuvering into position. On the bridge, Commander Eugene Wilkinson wears a heavy bridge coat over his uniform. Below, in the reactor compartment, the engineering watch team stands at their stations. They've trained for this moment for 6 months. Now it's real. Rear Admiral Rickover is aboard. Not as an observer, he'll remain for the entire sea trial, monitoring every system, questioning every decision. At 54, he spent 8 years building toward this moment. If Nautilus fails, the program fails. If the program fails, the Navy returns to diesel submarines and Rickover retires in disgrace. At 8 a.m., the reactor startup begins. The procedure is methodical, systematic. The same procedure they've practiced hundreds of times in Idaho, but now it's happening 30 feet underwater in a steel tube designed to submerge. The reactor operator verifies all conditions for startup. Primary coolant pumps, running. Steam generator water level, normal. Control rods, fully inserted. He receives permission from Commander Wilkinson and begins withdrawing control rods. The process is measured in inches. The control rods are pulled from the reactor core at precise intervals. Between each withdrawal, the crew waits. Watches neutron detectors. Monitors temperature. A nuclear reactor doesn't ignite like an engine. It gradually transitions from subcritical to critical as enough uranium atoms are positioned to sustain fission. At 9:47 a.m., the reactor goes critical. Neutron counters click steadily. Temperature begins rising in the primary coolant loop. The chain reaction is self-sustaining. The crew continues warming up the reactor, gradually increasing power. By 10:30 a.m., the reactor is producing sufficient steam for propulsion. Commander Wilkinson orders, "Single up all lines." Deck crew casts off all mooring lines except one forward and one aft. The tugboats push Nautilus away from the pier. The lines are released. At 11 a.m., Commander Wilkinson gives the historic order, "All ahead 1/3." The engine room responds, maneuvering answers, "All ahead 1/3." Steam flows from the reactor's steam generators to the main turbines. The turbines spin. The reduction gears convert high-speed turbine rotation to low-speed propeller rotation. The propeller bites water. USS Nautilus moves forward under her own power for the first time. Commander Wilkinson speaks into the radio, "Underway on nuclear power." 4 words. But those 4 words mean that diesel submarines, the apex of undersea warfare for 50 years, are obsolete. Everything changes. The Nautilus proceeds down the Thames River toward Long Island Sound. The reactor operates smoothly. Steam pressure is stable. The turbines run quietly. No diesel engine vibration, no generator noise. Just the hum of turbines and the rush of water past the hull. By 2 p.m., Nautilus reaches open water. The sea trial can begin. Commander Wilkinson orders a series of speed tests. All ahead 2/3. The reactor power is already at maximum. There's no throttle to advance. But steam flow increases. Nautilus accelerates. 10 knots. 12 knots. 15 knots. Submerged diesel submarines struggle to make 8 knots. Nautilus is going 15 knots on the surface, and she's designed for underwater operation. At 3 p.m. comes the critical test. Submerge. The diving klaxon sounds. Dive, dive. Vents open. Water floods into ballast tanks. Nautilus's bow angles down. The surface disappears above them. Depth gauges show 50 feet. 100 feet. 200 feet. The hull creaks as water pressure increases. These are normal sounds, steel compressing under load. But every man aboard is listening for abnormal sounds. A crack. A groan. Any indication that something is failing. At 250 feet, Commander Wilkinson levels off. All systems are nominal. No leaks. No problems. He orders, "All ahead full." Full steam flows to the turbines. Nautilus accelerates. 18 knots. 19 knots. 20 knots. Submerged. At a depth where diesel submarines crawl along on battery power, Nautilus is traveling faster than most destroyers can manage on the surface. The crew feels the difference immediately. This isn't a diesel submarine grudgingly submerging to hide. This is a vessel designed to live underwater. The ride is smooth. No surface wave action at 250 feet. The air is fresh. No need to snorkel, no battery gases. The reactor can maintain this speed indefinitely. Days, weeks, months. Rickover moves through the submarine, checking every space. He stops in the reactor compartment, watching gauges. Primary coolant temperature, 545 degrees Fahrenheit. Pressure, 2000 psi. Reactor power, 13,400 shaft horsepower. Everything exactly as designed. But he's not satisfied with exactly as designed. He questions the engineering watch. What's the temperature delta across the steam generators? The operator answers immediately. He's memorized the numbers. Rickover asks 3 more technical questions. The operator answers correctly. Rickover moves on without comment. Which, from Rickover, is high praise. The sea trial continues for 12 hours. Nautilus maneuvers at various speeds and depths. She performs emergency procedures, emergency blow to the surface, emergency stop, crash dive. Every system works. When Nautilus returns to Groton at midnight, she's proven that nuclear submarines aren't theoretical, they're real. Over the following months, Nautilus completed her shakedown cruise, the period where new ships work out problems and train crews. She traveled from New England to Puerto Rico, 1,381 miles, completely submerged. The trip took 84 hours at an average speed of 16 knots. A diesel submarine would have needed to surface or snorkel every few hours. Nautilus never broke the surface except to transmit her arrival message. The U.S. Navy suddenly had a vessel that could cross the Atlantic without surfacing, patrol indefinitely off Soviet coasts, and outrun any anti-submarine ship trying to hunt her. But this was just the beginning. Rickover wasn't satisfied with proving nuclear propulsion worked. He wanted to demonstrate that nuclear submarines could go places no ship had ever been. The Arctic Ocean in 1957 was the most mysterious place on Earth. The permanent ice pack covered 3 million square miles, an area larger than the continental United States. No surface ship could navigate it. Aircraft could fly over but couldn't see beneath the ice. Submarines could theoretically travel under the ice, but diesel boats lacked the endurance. The Arctic was strategically critical. It separated the United States and Soviet Union by the shortest distance. The Great Circle route from Moscow to New York passed over the North Pole. If the Soviets developed submarines capable of Arctic operations, they could approach America from the north, where radar coverage was sparse and naval bases were thousands of miles away. Rickover saw opportunity. Nautilus could transit the Arctic underwater, navigate beneath the permanent ice pack, potentially surface at the North Pole. It would be a navigation triumph, a scientific achievement, and a strategic demonstration that America controlled undersea domains the Soviets couldn't access. The mission was designated Operation Sunshine. Commander William Anderson, Nautilus's third commanding officer, received orders in early 1958 to prepare for Arctic operations. The challenges were extraordinary. Navigation under the ice meant no GPS. It didn't exist. No celestial navigation. They couldn't see the sky. No radio communication. Radio waves don't penetrate ice. They would navigate by dead reckoning and a primitive inertial navigation system that measured acceleration and calculated position. Accuracy after 1,000 miles, plus or minus 10 miles. In the Arctic, where ice keels extend hundreds of feet below the surface and polynyous, open water areas, are separated by dozens of miles, 10-mile navigation error could be fatal. If they surfaced into solid ice instead of open water, they'd be trapped. Battery reserves were limited. The reactor could run indefinitely, but electrical systems needed backup power. If ice blocked their path and forced them to backtrack, they might run out of reserve power before reaching open water. Commander Anderson trained his crew intensely. They practiced celestial navigation until every officer could shoot star sights in under 60 seconds. They drilled emergency procedures, ice collision, rapid ascent, loss of navigation systems. They studied bathymetric charts of the Arctic, memorizing underwater canyons and ridges that could serve as navigation references. On June 9, 1958, Nautilus departed Pearl Harbor on her first Arctic attempt. She transited northwest through the Bering Strait toward the Arctic Ocean. At the ice edge, she submerged to 400 feet and proceeded north. The journey was eerie. Sonar showed the ice canopy above, sometimes 10 feet thick, sometimes 40 feet. The underside wasn't flat, it was jagged, irregular, terrifying. Pressure ridges formed where ice sheets collided, extending downward like inverted mountains. Some pressure ridges reached 100 feet deep. Nautilus followed submarine canyons, deep underwater valleys that provided clearance between the sea floor and the ice above. Commander Anderson conned the ship personally, watching the fathometer showing depth below and the upward-looking sonar showing ice above. Sometimes the clearance was 300 feet. Sometimes it was 50 feet. On June 11th, disaster struck. The inertial navigation system failed. Without it, they had no reliable position fix. Dead reckoning alone wasn't accurate enough. Commander Anderson had no choice. Abort the mission. Nautilus reversed course and returned to Pearl Harbor. Rickover was furious. Not at Anderson, the decision to abort was correct, but at the navigation system failure. He ordered Westinghouse to rebuild the inertial navigator with triple redundancy. If one system failed, backups would activate automatically. Nautilus departed Pearl Harbor again on July 22, 1958. This time, the navigation systems worked perfectly. She transited through the Bering Strait, submerged at the ice edge, and proceeded north. The second attempt was methodical. Commander Anderson maintained 400 feet depth, following mapped underwater canyons. The crew tracked position by dead reckoning, inertial navigation, and occasional sonar fixes on known underwater features. Every calculation was checked 3 times. They discovered features no one had known existed. Underwater ridges that rose from 2,000-foot depths to within 50 feet of the surface. Submarine canyons 3,000 feet deep. Polyneus where the ice had cracked open, creating temporary leads of open water. On August 1, 1958, the navigation team calculated they were approaching 90 degrees north latitude. Commander Anderson ordered the ship to 150 feet depth and slowed to 5 knots. If they were going to surface at the North Pole, they needed to do it carefully. At 10:15 p.m., the navigation officer announced, "Captain, we are at 90 degrees north." Commander Anderson ordered, "All stop. Come to periscope depth." Nautilus rose. The upward sonar showed ice directly above, solid ice, 8 feet thick. Anderson tried moving 100 yards north. Still ice. 100 yards south. Ice, east, west. Ice everywhere. Finally, at 11:15 p.m. on August 3, 1958, Nautilus found a thin spot. Ice only 4 feet thick. Anderson ordered, "Break through." Nautilus rose slowly. The sail, the tower on top of the submarine, hit the ice. The ice cracked. The sail broke through into Arctic air. Commander Anderson raised the periscope. Through the eyepiece, he saw endless white in every direction. No landmarks. No features. Just ice extending to the horizon. They were at 90 degrees north latitude, the geographic North Pole. Anderson's message to Washington was brief: Nautilus 90 north. The transit under the Arctic ice pack covered 1,830 miles. Nautilus remained submerged for 96 hours. She proved that nuclear submarines could operate in the most hostile environment on Earth. She demonstrated that American submarines could patrol waters the Soviet Navy considered safe. Nautilus returned to a hero's welcome. President Eisenhower awarded the crew a Presidential Unit Citation. Commander Anderson received the Legion of Merit. The New York Times called it one of the great voyages of history. But for Rickover, the Arctic transit wasn't about glory, it was proof that his standards worked. Nautilus succeeded because her reactor was reliable, her crew was trained to perfection, and her systems were built to tolerances that allowed no failure. By 1960, the Navy was building nuclear submarines faster than shipyards could launch them. Skipjack-class submarines could sustain 30 knots submerged. Polaris submarines carried ballistic missiles capable of reaching Moscow from patrol areas in the Atlantic. The nuclear submarine force was becoming the Navy's primary strategic weapon. But building more submarines meant training more crews. And training more crews meant maintaining the standards that prevented accidents. By 1962, the United States Navy operated 26 nuclear submarines. The Skipjack-class boats were fast, 30 knots submerged. The George Washington-class ballistic missile submarines carried 16 Polaris missiles, each capable of delivering a nuclear warhead 1,200 miles. The attack submarine Triton had circumnavigated the globe underwater in 84 days, covering 41,500 miles without surfacing. Each submarine required a crew of approximately 100 officers and enlisted men. That meant the Navy needed 2,600 nuclear-trained personnel. By 1965, that number would double. By 1970, triple. The training program that Rickover built for Nautilus's crew, intimate, demanding, personally supervised, had to scale to thousands of students annually. Rickover's response: don't scale down the standards. Scale up the program. The Naval Nuclear Power School was established at Mare Island, California, and Bainbridge, Maryland. The curriculum was identical to what Rickover had designed for Nautilus's crew. 6 months of classroom instruction, 8 hours daily, 5 days per week, plus homework, plus weekend study. Students learned thermodynamics at a level comparable to university graduate programs. They calculated reactor criticality using neutron transport equations. They memorized the physical properties of materials, thermal conductivity, radiation damage resistance, corrosion behavior under high-temperature water. They studied heat transfer, fluid dynamics, electrical engineering, chemistry, and radiation biology. The instructors were officers who'd served on nuclear submarines and enlisted men who'd operated reactors at sea. They didn't lecture from textbooks, they taught from experience. When explaining steam generator operation, they'd describe what happened during actual casualties. When teaching reactor control, they'd reference real emergency procedures they'd executed. After 6 months of classroom training, students reported to one of 3 prototype sites: the S-1W in Idaho, Nautilus prototype; the S-3G in upstate New York, submarine and destroyer prototype; or the A-1W in Idaho, aircraft carrier prototype. For 6 months, they stood watches as reactor operators. They performed every procedure they'd studied: startup, shutdown, power changes, emergency procedures. The prototype training was where theory became muscle memory. Students didn't just know how to respond to a loss of primary coolant pumps. They'd actually shut down the reactor using emergency procedures while alarms sounded and instructors simulated additional casualties. They didn't just understand steam plant operation. They'd operated the turbines, adjusted feedwater systems, and maintained condenser vacuum during simulated emergencies. The failure rate remained approximately 25%. 1/4 of students who entered the program didn't complete it. Not because they were unintelligent, many had college degrees, but because they couldn't maintain Rickover's standard of absolute technical competence under pressure. Rickover personally interviewed every officer who completed nuclear training. These interviews were legendary. One officer recalled Rickover asking, "Why is the primary coolant loop maintained at 2000 psi?" The officer explained that high pressure prevented boiling, allowing operation at 550 degrees Fahrenheit. Rickover asked, "Why not 1800 psi?" The officer explained that safety margin was required for pressure transients. Rickover asked, "Calculate the pressure transient during a reactor scram with loss of pressurizer spray." The officer couldn't. That calculation required complex transient analysis. Rickover ended the interview. The officer was sent back to prototype training for 3 more months. This level of rigor created something unprecedented. A safety culture so thorough that between 1954 and 1970, U.S. nuclear submarines operated for millions of miles without a single reactor accident. 0 radiation releases that harmed crew members. 0 reactor core damage. 0 reactor-related fatalities. Compare this to the Soviet nuclear submarine program, which began shortly after America's. The Soviets built their first nuclear submarine, K-3 Lenensky Komsomol, in 1958, 3 years after Nautilus. The K-3 design was innovative, but Soviet training standards were lower. Reactor operators received months of training, not years. Safety culture emphasized production quotas, not perfection. The consequences were predictable. In 1961, the Soviet submarine K-19 suffered a loss of coolant accident while submerged. The primary coolant system developed a leak. Without cooling, the reactor core began overheating. 8 crew members, engineers and officers, entered the reactor compartment to jury-rig a cooling system using emergency equipment. They succeeded, preventing core meltdown. All 8 died from radiation exposure within weeks. In 1968, the Soviet submarine K-27 suffered a reactor control failure. Radiation levels in the reactor compartment exceeded lethal doses. 9 crew members died. The submarine was taken out of service, sealed, and eventually scuttled. Between 1961 and 1980, Soviet nuclear submarines experienced at least 14 reactor accidents serious enough to cause crew casualties or require premature decommissioning. 2 submarines, K-8 in 1970 and K-219 in 1986, sank due to reactor-related casualties. The difference between American and Soviet programs wasn't technology. Soviet reactor designs were often innovative. The difference was culture. The culture Rickover built. The culture that treated nuclear power as requiring perfect discipline, perfect training, and perfect maintenance. That culture was expensive. It required paying nuclear-trained sailors more than conventional sailors. It required longer training pipelines, which meant smaller crews available for deployment. It required maintaining standards that made some admirals uncomfortable. Rickover would relieve a submarine commanding officer for procedural violations that other communities considered minor. But the cost was justified by results. By 1970, American nuclear submarines dominated underwater warfare. They could detect Soviet submarines before being detected. They could outrun Soviet anti-submarine ships. They maintained continuous deterrent patrols, ballistic missile submarines always at sea, always ready, making a Soviet first strike impossible to execute without guaranteed retaliation. And they did it without killing their own crews through preventable accidents. January 27, 1970. Hyman Rickover's 70th birthday. Under Navy regulations, this was his mandatory retirement date. Flag officers could serve until age 64. Rickover had received multiple 2-year extensions, unprecedented, but justified by his unique role overseeing nuclear propulsion. Now, at 70, those extensions had run out. The Navy prepared his retirement ceremony. His replacement was selected, a capable officer with nuclear training and better interpersonal skills. Congress prepared testimonial resolutions. Defense contractors prepared plaques and awards. Rickover prepared nothing. He came to work on January 28, 1970, at 7 a.m., same as always. Sat at his desk in the Naval Reactors office. Reviewed technical reports. Signed letters. When asked about retirement, he stated simply, "The work isn't finished." The Navy was caught off guard. Retirement wasn't optional. It was mandatory. But Rickover had spent 24 years building relationships with Congress. And Congress had the authority to extend his service indefinitely through special legislation. Representative Charles Bennett from Florida introduced a bill extending Rickover's service for 2 more years. The justification was straightforward. The Navy was transitioning to an all-nuclear submarine force. New reactor designs needed approval. Training standards needed maintenance. Safety oversight required someone who understood nuclear power at a fundamental level. The bill passed. Rickover remained on active duty at age 70. 2 years later, in 1972, the same process repeated. Rickover turned 72. Congress passed another extension. The Navy's leadership was furious, but helpless. Rickover had made himself indispensable. He used those years to expand his empire. By 1975, the Navy operated 131 nuclear submarines, the entire submarine force except for a handful of diesel boats maintained for special operations. Nuclear-powered cruisers were entering service. Nuclear-powered aircraft carriers, starting with USS Enterprise in 1961, followed by Nimitz in 1975, were becoming the fleet's capital ships. Every nuclear reactor in the Navy required Rickover's approval. Every commanding officer of a nuclear-powered vessel was personally interviewed by Rickover. He was 75 years old and maintained the same 18-hour workdays he'd worked at 45. His interviews with prospective commanding officers remained legendary. In 1973, Lieutenant Jimmy Carter, a Naval Academy graduate and nuclear submarine officer, interviewed with Rickover for command of a new nuclear submarine. The interview lasted 2 hours. Rickover asked Carter about his academy performance. Carter mentioned he'd graduated 59th out of 820, top 10%. Rickover asked, "Did you always do your best?" Carter, eager to impress, replied, "No, sir, I didn't always do my best." Rickover leaned back in his chair and asked a question that would haunt Carter for years: why not? The interview ended shortly after. Carter didn't get the command. His father's death forced him to resign from the Navy to manage the family farm. But that question, why not, became central to Carter's philosophy. When he ran for president in 1976, he titled his campaign autobiography, "Why Not the Best?" directly referencing Rickover's challenge. By 1977, Carter was President of the United States. One of his first acts was signing legislation extending Rickover's service again. Rickover was 77 years old. He'd served 57 years in the Navy, longer than most people live, and he showed no signs of slowing. He testified before Congress regularly, usually to criticize something. Defense contractors were cutting corners. The Navy was lowering training standards. Nuclear power plants were being built by companies that didn't understand reactor safety. Rickover had spent 30 years building a culture of perfection, and he saw it eroding. In 1979, the 3 Mile Island nuclear accident occurred, a partial meltdown at a commercial reactor in Pennsylvania. No one died, but the accident terrified the public and nearly destroyed the commercial nuclear power industry. Rickover testified before Congress about the accident. His message was blunt: commercial nuclear power failed because civilian operators didn't maintain Navy standards. The Navy's safety record is perfect because we assume every operator is fallible, every component will eventually fail, and every procedure must be tested under worst-case conditions, he testified. Civilian power plants cut costs by assuming nothing will go wrong. That assumption killed 3 Mile Island. By 1981, Rickover was 81 years old. He'd served under 13 presidents, from Calvin Coolidge to Ronald Reagan. He'd built the nuclear navy from nothing to 180 nuclear-powered ships. He'd trained 10,000 nuclear operators. He'd maintained a perfect safety record for 27 years. And he still came to work every day at 7 a.m. But change was coming. Ronald Reagan's administration brought a new Secretary of the Navy, John Lehman. Lehman was 38 years old, 43 years younger than Rickover. He was ambitious, politically savvy, and determined to modernize the Navy's leadership structure. Lehman believed Rickover's dual-hatted position, reporting to both the Navy and the Department of Energy, gave one man too much power. Rickover could overrule the Chief of Naval Operations. He could block reactor designs favored by admirals. He could relieve submarine commanding officers without consulting their chain of command. Lehman also believed that Rickover's management style, confrontational, demanding, abrasive, was outdated. The Navy needed leaders who could build consensus, not dictators who demanded perfection. On January 31, 1982, Lehman called Rickover to his office. The meeting lasted 15 minutes. Lehman informed Rickover that his service would end January 31, 1982. No extension would be requested from Congress. No appeal would be considered. Rickover asked, "Is this optional?" Lehman replied, "No, sir, it is not." Hyman G. Rickover, Admiral, United States Navy, retired February 1, 1982, after 63 years of service. The longest-serving officer in U.S. military history. His retirement ceremony was small. He refused a large event. He received the Medal of Freedom from President Reagan. He shook hands with officers he'd trained. He walked out of the Naval Reactors building for the last time at 5 p.m., carrying a box of personal papers. The next day, someone else sat at his desk. Someone else reviewed reactor designs. Someone else maintained safety standards. The culture Rickover built would continue. But the man who built it was gone. Hyman Rickover spent his final years writing, testifying before Congress about education reform, and criticizing what he perceived as declining American standards. He published articles arguing that American schools had stopped teaching discipline, that universities emphasized theory over practical knowledge, and that society had become too tolerant of mediocrity. He died July 8, 1986, at age 86, at his home in Arlington, Virginia. The funeral was private. No military ceremony. No speeches. He was buried at Arlington National Cemetery in a grave marked simply with his name and rank. No list of accomplishments. No inspirational quotes. But his legacy is measured not in words on a tombstone. It's measured in numbers that tell an extraordinary story. As of January 2026, the United States Navy has operated nuclear submarines for 71 years. In that time, American nuclear-powered vessels have traveled hundreds of millions of miles. They've operated under Arctic ice, in tropical shallows, at depths exceeding 1,000 feet, and in every ocean on Earth. They've maintained continuous deterrent patrols throughout the Cold War and into the 21st century. Ballistic missile submarines always at sea, always ready, making nuclear war less likely because retaliation is certain. The safety record remains perfect. Not one American nuclear submarine has ever experienced a reactor accident that released radiation beyond the vessel. Not one crew member has ever died from reactor operations. Not one reactor core has ever suffered damage severe enough to require emergency shutdown. This record is unprecedented in the history of nuclear power, military or civilian. Compare that to other nations' programs. The Soviet Union, later Russia, operated nuclear submarines for 60 years. They experienced at least 14 serious reactor accidents. The K-19 accident in 1961 killed 8 crew members from radiation exposure. The K-27 accident in 1968 killed 9. The K-431 refueling accident in 1985 spread radiation across a naval base, contaminating hundreds of workers. 2 Soviet submarines, K-8 and K-278 Komsomolets, sank due to reactor-related fires and casualties. France operates nuclear submarines with an excellent safety record. They learned from American procedures and adopted similar training standards. Britain's nuclear submarine program, developed with American assistance, also maintains high safety standards. China's nuclear submarine program has experienced at least 2 serious accidents, though details remain classified. The difference isn't technology. Soviet reactor designs were often innovative. Liquid metal-cooled reactors, lead bismuth eutectic coolant systems, advanced control mechanisms. The difference is culture. The culture Rickover built. The culture that treats nuclear power as simultaneously indispensable and dangerous. The culture that demands perfect training, perfect procedures, and perfect discipline. That culture survived Rickover because he institutionalized it. The Naval Nuclear Propulsion Program, officially called Naval Reactors, part of the Department of Energy and the Department of the Navy, continues to operate under principles Rickover established in 1948. Every officer who serves on a nuclear-powered ship must complete Naval Nuclear Power School and prototype training. The curriculum is essentially unchanged from what Rickover designed. 6 months of classroom instruction followed by 6 months operating a prototype reactor. The failure rate remains approximately 20 to 25%. Standards haven't been lowered to increase graduation rates. Every commanding officer of a nuclear-powered vessel must receive personal approval from the Director of Naval Reactors. The interview process is rigorous. Technical knowledge is tested, judgment is evaluated, temperament is assessed. Officers who don't meet standards don't get commands, regardless of their political connections or career accomplishments. Safety protocols remain absolute. Any radiation exposure above natural background levels is investigated. Any procedural violation results in immediate relief from watchstanding duties pending investigation. Any equipment failure requires root cause analysis before the reactor returns to operation. The program has produced remarkable officers. 72 nuclear submarine commanding officers eventually became admirals. Hundreds more became successful engineers, scientists, and business leaders in civilian life. They carried Rickover's philosophy into civilian careers: assume nothing, test everything, accept no excuses. USS Nautilus, the submarine that started it all, was decommissioned March 3, 1980, after 25 years of service. She'd traveled 513,550 miles, enough to circle the Earth 20 times. She'd operated on 6 of 7 continents. She'd spent 6,320 hours submerged. She'd proven that nuclear propulsion could work reliably for decades. Nautilus is now a museum ship in Groton, Connecticut, preserved at the same Thames River location where she was launched in 1954. More than 250,000 visitors tour her annually. They walk through cramped crew quarters where 116 officers and men lived for months at a time. They see the control room where Commander Wilkinson gave the order, "Underway on nuclear power." They stand outside the sealed reactor compartment, still slightly radioactive from 25 years of operation. The reactor compartment will remain sealed forever. When Nautilus was decommissioned, the Navy considered 3 options: remove the reactor and dispose of it, cut out the entire reactor section and bury it, or seal it permanently. They chose to seal it. The reactor is defueled. The uranium has been removed. But the reactor vessel and internal components remain radioactive from decades of neutron bombardment. The activity level is low, safe for visitors who don't enter the compartment. But it serves as a permanent reminder: nuclear power demands respect. In January 1954, when First Lady Mamie Eisenhower christened USS Nautilus at Groton, Connecticut, the United States Navy had 0 atomic submarines. The submarine force still operated diesel-electric boats, vessels that were really surface ships capable of temporarily hiding underwater. They ran on batteries while submerged, traveling slowly for limited time before needing to surface or snorkel to recharge. The idea that a submarine could remain submerged for months, travel at 20+ knots deep underwater, cross oceans without surfacing, and operate for years without refueling, that was science fiction. Respected naval officers said it was impossible. Scientists said the engineering challenges were insurmountable. Congress questioned whether money should be spent on theoretical technology when conventional submarines worked adequately. One man made it real. Not through brilliance alone. Many scientists and engineers were more brilliant. Not through political connections. He had none when he started. Not through charm. He possessed very little. Through relentless, obsessive, uncompromising dedication to a vision that others couldn't see. Hyman Rickover was difficult to work for. Abrasive in meetings. Impossible to satisfy. He made enemies of admirals who should have been allies. He alienated contractors who could have made his life easier. He demanded perfection from subordinates who were already working 16-hour days. He was passed over for promotion because the Navy's leadership didn't think he fit the image of what a flag officer should be. But he changed naval warfare more profoundly than any officer since the introduction of steam power. He built technology that gave America strategic superiority for half a century. He created a safety culture so rigorous that 71 years later, it remains the gold standard for nuclear operations worldwide. He proved that excellence isn't about accepting what's possible. It's about making the impossible inevitable through discipline, knowledge, and refusal to compromise. On January 21, 1954, Nautilus slid into the Thames River. On January 17, 1955, she went underway on nuclear power. Those two dates bracket the moment when naval warfare changed forever. When submarines stopped being submersible ships and became true underwater vessels. When deterrence became credible because retaliation was certain. When one man's vision became the foundation of American maritime superiority. That's the legacy of the admiral who wouldn't retire, the engineer nobody wanted, and the immigrant kid from Chicago who refused to accept that good enough was ever good enough. His standards remain. His culture endures. And 71 years after Nautilus proved the impossible was possible, the nuclear navy he built continues to operate with 0 reactor accidents, a safety record unmatched in any nuclear power program in human history. That's not luck. That's not coincidence. That's the result of building something right the first time, maintaining standards that never decline, and remembering that excellence isn't an achievement. It's a habit that must be practiced every single day.